All right, guys, welcome. Good morning. Let's see here. If I pull up the calendar for kind of where we're at and where we're going. This week's focus covers hypothesis testing for the difference in two means. We had a quiz last Thursday. Those of you who finished the quiz should have gotten some feedback from me. I got those graded and returned to you. We have two more quizzes plus the course final to round out the year. I got a quiz for next Thursday, the 30th, on differences in two means hypothesis testing and what we'll cover next week when it comes to paired inference, paired T confidence intervals and hypothesis testing. For now, let's go ahead and get started with this. And once again, this is difference in two means hypothesis testing. Okay, so the question here in the top left corner reads as this. The city of Van Meter is concerned about home prices compared to the surrounding areas. A random sample of 50 homes shows an average value in Van Meter of $191,000 with a standard deviation of $32,000. The average home value for 50 homes selected in random neighboring communities was $179,000 with a standard deviation of $17,000. Is this enough evidence to suggest that home values are higher in Van Meter than in surrounding communities? Use a significance level of alpha equals 5%. So let's first define our two groups. I'm going to call group 1 Van Meter, and group 2 kind of the neighbor. The neighboring communities. We can see that in Van Meter, a sample of 50 homes has an average home value of $191,000 with a standard deviation of $32,000. So the sample mean for group 1 Van Meter was 191,000. I'm just going to call it 191 and measure everything in terms of thousands. The standard deviation in that sample of homes was 32,000. For a sample size of 50 homes. For the surrounding neighboring communities, we had a sample average home of 179,000. With a standard deviation of 17,000. And the same size sample, 50 homes. All right, let's go ahead and first check our conditions. We have to have a random sample of homes that represents 10% of the population with an independent sample of at least 30 homes for two large means. So it says we have a random sample of homes. We have 50 homes in Van Meter and 50 homes in the surrounding neighboring communities. I think that represents less than 10% of all homes in Van Meter and the surrounding communities. And we have 50 of each, so that would be enough for an independent sample. So I'm going to go ahead and write that conditions are satisfied. Okay, let's now go ahead and define our null and alternative hypotheses. We're trying to test to see if that we have evidence to suggest that home values are higher in Van Meter than in the surrounding communities. So for our null hypothesis, let's assume that they are equal. And let's, for our alternative hypothesis, say that group 1 Van Meter average home price is greater than group 2, the average price in the surrounding communities. We'll set up our rejection region. We're using a significance level of 5%, leaving the other 95% in the remaining part of the distribution. I know that we have a upper tail that I've shaded in here. What is the t-score that cuts off that top 5% from the remaining 95%? Once again, it's worth noting that I have a specific number of degrees of freedom. The degrees of freedom is sample size 1 plus sample size 2 minus 2 for the two independent samples. So 50 plus 50 minus 2 makes 98. So a couple of things we can do. Estimate that would be to use a t-table. And so I can see I have a one tail, 5% significance level here in this t-table in the second left-handed column. If I go down, 98 is pretty close to 100 degrees of freedom here in this row towards the bottom. And I see a t-score of about 1.66. Another option, if I open up Google Sheets, is to type into some cell equals t.inv. And it says probability. Well, that would be the 95% that it is to the left for 98 degrees of freedom. And I get about the same 1.66 either way. 1.661 if you want to round up. The larger the sample, I go back to my t-table, the larger the sample, the less incremental change. The difference in the t-scores from 25 to 26 is larger than the difference in the t-scores from like 250 to 400. There's less incremental change for the larger sample sizes. Anyway, 1.66. If we can calculate a t-score that's more extreme than 1.66, we have significant results. And that t-score formula is the difference in the means based off of our sample. X bar 1 minus X bar 2 divided by the square root of the variance, S sub 1 squared divided by N1 plus S sub 2 squared. S sub 2 squared divided by N2. All right, so let's go ahead on the next page and get this set up. We have 191 minus 179. Divided by the square root of 32 squared over 50 plus 17 squared over 50. I think it was 17 that I just read. Double check that. Yep. All right, here's the t-score for our sample of homes in Van Meter and their surrounding communities. Go ahead and type this into Desmos. Make sure I got that right. 191 minus 179. Yep. And I see a t-score of about 2.342. 2.342. So what should our decision be? Well, 2.342 lies in that shaded region. It's further to the right, greater than 1.66. So we have more extreme results than the cutoff region that we already got set up. Our decision should be to reject the null hypothesis. Our evidence suggests that home prices are greater in Van Meter than in the surrounding communities. Can't spell that right. The last thing we'll do is to find the p-value. You'll need to use sheets for this. And the coding is equals t-dist in some blank cell. We'll need three things: the t-score, the degrees of freedom, and the number of tails. So back to this, we had a t-score of 2.342 for 98 degrees of freedom and 2 tails. And I see a p-value, probability of 0.0212. And the p-value is the probability of our sample, or sample more extreme, if the null hypothesis were true. So if it was true that home prices in Van Meter and the neighboring towns were the same, I'd collect a sample such as the one we had in our question only 2% of the time. So that is rare enough for us to assume that they are no longer the same in terms of the home prices. Home prices are greater in Van Meter than in the surrounding towns. Questions there, guys? If anything, go ahead and speak up. Let me know, please. Check the chat here really quick. No? Okay. Okay. I did have one more question. For us to look at here this morning. It says Hy-Vee is concerned about product placement within aisles of their stores. They decided to track Coca-Cola sales in stores displaying in the middle of an aisle and at the end of the grocery aisle. So imagine for a second that they place the Coca-Cola bottles in the middle of the aisle and at the end of the aisle when you first come up and down the the aisle of the grocery store. Where are people more likely to buy Coke? When it's placed in the middle of the aisle or at the end? That's what Hy-Vee's trying to determine. So 10 stores are chosen randomly, and they sold an average of 50 bottles of Coke with a standard deviation of 14 bottles when displayed at the end of the aisle. So at the end of the aisle, we had 10 stores with an average of 50 bottles sold, standard deviation 14. 10 more random stores were chosen, and they displayed the Coke. Oops, let me say that this is that's a quick typo when I was typing this up. Let's say that this is the middle of an aisle. Right there. 10 random stores displaying Coke in the middle of an aisle sold 58 bottles with a standard deviation of 12 bottles of Coke. Is this enough statistical evidence to suggest a difference in Coke sales when displayed at the end of the aisle compared to when being displayed normally? Normal meaning in the middle of the aisle. So let's go ahead and write down our data. I'm going to call group 1 the end of the aisle. And group 2 the middle of the aisle. So in group 1, we had 10 stores, sell 50 bottles on average, standard deviation of 14. For group 2, in the middle of the aisle, they sold 58 bottles with an average standard deviation of 12 for the 10 stores. For our conditions, we chose stores randomly. I think that 10 of each is less than 10% of all stores that sell Coke. So we'll say that our conditions have been satisfied. We chose stores randomly. 20 stores in total is less than 10% of all stores. So we have a random independent set of samples. For our hypotheses, this is slightly different because we're just testing to see if there's a difference in Coke sales when being displayed at the end of the aisle when compared to being displayed normally. So I don't know if one's greater than the other. I'm just testing to see if there's a difference. So for our hypotheses, let's assume that the average sales of Coke in the two stores are the same. For our null hypothesis, and then test to see if there is a difference in the average Coke sales between the two stores. So null hypothesis, they are equal. Alternative hypothesis, the average sales of Coke bottles are not equal. So rather than the one-tailed test in the previous question, now I have a two-tailed test. Since we weren't given a significance level, Let's assume 5% again. So I have the 5% cut into the two rejection regions to the left and right, with 95% in the middle. We have a specific number of degrees of freedom. 10 from group 1, 10 from group 2 makes 20, minus 2 to make 18. And what is the t-score? That separates the middle 95% from the upper or lower 2.5%. So on our t-table, we'll be in the middle column because I'm using a two-tailed test at the 5% significance level. 18 degrees of freedom gives me a t-score of 2.101. And once again, that test statistic formula, I'll write it again, is the difference in our sample means divided by the variance. So starting our test statistic, 50 minus 58. Divided by the square root of 14 squared over 10 plus 12 squared over 10. I'll go on the Desmos and get this typed in. It was 50 minus 58. Of 14 squared divided by 10 plus 12 squared divided by 10. Gives me negative 1.37. 1.372 if I round up. Now, if I carefully write this in here, t equals negative 2.101 would be the same on the lower left tail. That would be, for our t-score, not as extreme. Negative 1.372 is closer to 0 than negative 2.101. So we would, in this case, fail to reject the null hypothesis. Our evidence, or we lack evidence, pardon me, to suggest a difference in sales of Coke when bottles are displayed at the ends of an aisle or in the middle of an aisle. this t-score was not as extreme than the ones defined by our rejection region, plus or minus 2.101. Okay, so for our p-value, we'll go back to Sheets. And t-dist. Now the way Sheets does this is that it always wants you to input a positive t-score, 1.372. The area above positive 1.372 would be the same as the area below negative 1.372. So in the eyes of Google Sheets, there really is no difference between a positive or negative t-score. So 1.372 with 18 degrees of freedom and 2 tails gives me 0.1869. If you did put negative in there, you would get an error message, and it says that it should be positive or 0. So it would tell you what you did wrong, and you would just fix it. It's pretty simple. So let me fix this. Clicked one too many things. 0.1869. Now, if the P is low, we reject the HO. So a little bit different than the first question. Our p-value is higher than our significance level. We only want to reject a true null hypothesis 5% of the time. This would be greater than that, so we lack statistical evidence. If the Coke bottle sales were the same, no matter where they were displayed, I would find a sample such as mine 18.69% of the time. So not uncommon enough for us to reject the null hypothesis. Questions on these couple examples, guys? Okay, we'll do some more practice of this on Wednesday. Those of you who are missing some quizzes from earlier or would like to reassess a quiz from before spring break, before we started going to distance learning, please reach out to me and let me know. We can do some review together and set up a time for you to reassess whatever you'd like. Other than that, I think we'll call it a day. So have a good rest of your day. Have a good afternoon, guys. Take it easy.